Okay, let's dive into the incredible explosion we're seeing in 3D digital worlds and the tech that actually brings them to life.
Right.
Specifically, how we manage to render these, super complex scenes from basically any viewpoint and do it in real time.
Yeah, and for a while now, a big player in making that happen has been 3D Gaussian Splatting, or 3D
The
GLs.
3GS, right. It really was a breakthrough, wasn't it?
hmm
Enabling that kind of fluid, real-time view synthesis.
Absolutely. It kicked off a whole wave of new research. It represents scenes as collections of 3D Gaussians
Okay.
and uses this clever splatting process to project them onto the image plane. Its speed really made it foundational for things like neural rendering, autonomous driving systems, even generating 3D assets.
But like often happens, our sources point out that even with all that success, 3D GS isn't quite the end of the story.
Mm-hmm.
It sounds like you can sometimes struggle to capture really fine details efficiently.
That's one part, yeah. The sources talk about insufficient expressivity sometimes.
And the other thing is, it often needs a massive number of those Gaussian components to build a scene well.
Exactly. Which sounds like a parameter efficiency issue, right? Lots of components needed.
Yeah, low parameter efficiency, that's what the sources call it.
Highlighted in quite a bit of recent work, actually.
So this deep dive is all about a new model proposed in our source material that aims to tackle those very problems head on.
It's called Student Splatting and Scooping, or SSS for short.
SSS, okay.
So our mission today is to really unpack what SSS is, understand how it fundamentally differs from 3D GS. It actually revisits its core ideas.
Oh, interesting.
And then see what the results they reported tell us about its potential, for novel view synthesis and just 3D representation generally.
All right, let's jump in then. How does SSS propose to do things differently? You said it starts by reimagining the core of 3D GS.
It does.
We briefly mentioned it, but maybe a quick refresher. What's the fundamental mechanism behind the original 3D GS again?
Okay, so at its core, 3D GS models a scene as basically an unnormalized mixture of 3D Gaussians.
Right.
The key is projecting these 3D Gaussians onto the 2D image plane using something called differentiable rasterization.
Differentiable rasterization.
Yeah.
That sounds technical. Is it basically just rendering the 3D math onto a 2D image in a way that lets the AI learn from it?
Precisely. That's a great way to put it. It allows the gradients, the learning signals, to flow back, making it trainable end to end.
Okay.
And the speed comes because Gaussians have these really convenient mathematical properties, analytical forms for the transformations needed during rendering.
Which makes things fast.
Yeah, enabling those very fast forward and backward passes, crucial for real-time performance and, efficient learning.
Got it. So represent the scene with Gaussians, project them quickly in a way the network can learn from. Simple enough.
Well, conceptually.
Right. Now, the SSS philosophy, as you mentioned, seems to challenge that assumption that it has to be just Gaussians and just adding things together.
It really does.
Yeah.
The researchers behind SSS basically argue that the underlying principle is fitting a 3D mixture model. Okay. But that model doesn't have to be restricted to only Gaussians. And the splatting part doesn't have to be purely additive.
Additive meaning just layering positive things on top of each other.
Exactly. They believe operating only in that positive density space, like traditional mixture models usually do, is actually suboptimal.
Okay, that sounds like a pretty fundamental shift.
Yeah.
So what's the first big change they propose?
Yeah. The first big change is the building block itself. They replace Gaussians with student T distributions.
The student's T. Okay.
And initially, they look at the case with 1 degree of freedom, which is actually the Cauchy distribution.
Cauchy, right. Why that change? What does the T distribution give you?
Well, the student's T distribution is a more flexible generalization of the Gaussian. Crucially, it has this learnable parameter. That's the Greek letter nu. It's the degree of freedom.
Like a dial or a slider you can adjust.
Exactly like that. So as the source shows in one of its figures, with e close to 1, you get that fat-tailed Cauchy distribution.
Fat-tails meaning it spreads out more.
Yeah, it doesn't drop off as quickly as a Gaussian. But as K gets really large, approaches infinity, it actually converges back to the familiar thin-tailed Gaussian. And by making learnable for each component in the scene, the model can adapt the tail thickness, or you could think of it as the spatial influence of that specific component.
And the benefit of having those fatter tails, like the Cauchy distribution offers.
Well, a fat-tailed distribution can cover a larger area with comparatively higher densities than a Gaussian would with the same variance.
Okay.
So the source points out this hints, right, at the possibility of needing fewer components overall to represent the scene accurately.
Because each one can potentially do more work, cover more ground efficiently.
Exactly. And importantly, just like Gaussians, these t-distributions also maintain useful analytical forms for the kind of transformations you need during rendering affine and projective transformations.
So you keep that speed advantage.
Yeah, pretty much. The math still works out nicely as they show in their equations, so you still get fast rendering.
Okay, so step 1, more expressive components using t-distributions that can potentially cover space more efficiently. What about the second big change, this idea of splatting and scooping?
Right. This is where the scooping comes in. They were inspired by some work on what are called non-monotonic mixture models.
Non-monotonic.
Meaning they don't just go up, they can go down too. So SSS introduces the ability for components to have negative densities.
Negative density. Wait, so alongside the positive component splatting or adding color and density, you have negative component scooping or effectively subtracting it.
That's exactly it. Subtracting color or density.
That feels weird. How does subtracting help when you're trying to build up a scene representation out of light and color?
It sounds strange at first, I know, but the sources explain it provides this really powerful subtractive capability that turns out to be incredibly efficient for representation.
How so?
Think about representing a shape with a hole in it. They use a torus, like a donut, as an example in one figure.
Okay, a donut shape.
With only positive components, like standard Gaussians, accurately defining that empty space, the hole in the middle requires a lot of Gaussians clustered around the edges of the hole, trying to carve it out implicitly.
Right, you need a bunch to define the boundary.
What if you just used one big positive component covering the whole donut area, solid, and then put one negative component right in the middle, scooping out the density?
So it directly carves out the hole.
Exactly. You can define that hole much more efficiently. The source says just two components, one positive, one negative, can represent that torus topology really well.
Compared to needing way more positive ones.
Yeah.
That directly addresses that parameter efficiency problem we talked about.
Precisely. It's a strong argument for their claim that operating only in positive density space is suboptimal. Sometimes subtraction is just more efficient.
Okay, so we've got these more flexible components, the t-distributions, and the ability to both add density with splatting and subtract it with scooping. But combining learnable tail thickness and positive-negative densities, that sounds a lot more complex to manage than just dealing with positive Gaussians.
It definitely is.
How does SSS handle the learning, the optimization process?
Yeah, that's the third core piece.
Yeah.
The researchers found that with this added complexity, especially that learnable and in the introduction of negative components, standard optimization methods, like simple stochastic gradient descent, kind of struggled.
Struggled how?
Well, the parameters like the position and the covariance, the shape size, become more tightly coupled.
Parameter coupling. What does that mean exactly?
It basically means the different settings of a component, its shape, size, position, tail fatness, whether it's adding or subtracting, weren't learning independently as well as they needed to. They weren't exploring the possibilities broadly enough. SGD, the standard method, could just get stuck in, local minima, bad solutions.
So they needed a different, maybe smarter way to train this whole thing.
Yes. They propose using a principled sampling approach called stochastic gradient Hamiltonian Monte Carlo, or SGHMC.
SGHMC. Okay, that's a mouthful. What does it do?
Well, the source explains SGHMC helps mitigate this parameter coupling issue by exploring the parameter space much better.
How?
Think of it like giving the learning process some momentum and also injecting a bit of controlled noise. It's like navigating a hilly landscape. SGHMC helps the search process roll over small hills and explore different valleys instead of just getting stuck in the first dip it finds. They talk about using concepts like friction and noise to guide it.
Okay, so it helps it avoid getting stuck and find better overall solutions for all those interacting parameters.
Exactly.
And does that specifically help with learning that tail thickness parameter that we talked about?
It absolutely does. There's a figure in the paper, figure 4, that shows a really clear distinction. When they use SGHMC, the model learns a wide distribution of values across all its components.
Meaning it's actually using the flexibility?
Yes. It's fully utilizing the t-distribution's adaptability. But when they tried a standard optimization approach similar to what 3DGS uses,
What happened?
the learned values were heavily concentrated, mostly stuck near one value. It just couldn't explore or leverage the full potential of the t-distributions. SGHMC was key to unlocking that.
Interesting. And they also mentioned something about components that become almost transparent. They don't just delete them.
Right, that's another neat trick. Instead of simply deleting components that have very low opacity, become near transparent.
Which happens during training, right?
Yeah, components might become redundant, so instead of just removing them, they get recycled.
Recycled how?
They're relocated to the location of a different high-opacity component. But it's done carefully to minimize the change to the overall scene's color and density. There are some equations defining how they do this smoothly.
Why do that instead of just deleting?
The idea is it helps improve sampling stability and mixing during the SGHMC process. Relocating, especially with a little nudge they call sign perturbation for negative components, makes the learning process more robust, less likely to get disrupted by components suddenly disappearing.
Okay, that makes sense. Keep things stable. All right, so the recipe is flexible t-distributions for adaptive shape.
Check.
Positive and negative components for efficient representation via splatting and scooping.
Check.
And a smart sampling method, SGHMC, combined with recycling for robust learning.
That's the core of SSS.
Got it. So let's talk results. How did SSS actually perform when they put it to the test against other methods?
Okay, so the sources describe pretty extensive evaluations. They used multiple standard data sets that are common in this field: MIPNER 360, tanks and temples, deep blending.
The usual suspects.
Right. And they compared SSS against the original 3DGS and also several state-of-the-art variants using the standard image quality metrics, PSNR, SM, and LPIPS. You know, the common ways to measure how close the rendered image is to the real one.
And the big picture findings on quality. How did it stack up?
Overall, SSS achieved either the best or second best results on most of those metrics across the different data sets. They have a big table, table 1, showing...
Oh, it's top-tier quality.
Yeah. And in some scenes, the lead was actually quite significant compared to whatever the next best method was. For instance, they call out the train scene from the tanks and temples data set.
Okay.
There, SSS showed really notable improvements across all three metrics: PSNR, SM, and LPIPS compared to the second best performer.
So it matches or even beats the state-of-the-art in visual quality. That's impressive. But where it really seems to make waves based on the sources is that parameter efficiency thing we keep coming back to.
Absolutely. This is maybe the most compelling finding they report. SSS demonstrates much, much higher parameter efficiency. Meaning it can achieve comparable and often better quality than other methods while using significantly fewer components. Fewer building blocks.
How much fewer?
The source gives a really striking number, achieving comparable results while reducing the number of components by as much as 82% in some scenes.
82%? That's a huge reduction.
It's a staggering reduction, and Figure 4 in the paper visually supports this across different data sets. It shows SSS maintaining higher quality scores, higher PSNR, than other methods, even when it's forced to use significantly fewer components compared to what those other methods normally use.
Wow. Okay, let's try and make that more tangible. They provide visual examples in the sources, right? What specific details does SSS capture better, especially when it's using far fewer components?
Yeah, the qualitative comparisons, the pictures are really compelling. Figure 3 shows several examples where SSS does a better job capturing fine geometric and textural details.
Like what kind of details?
Things like the indentations on a box lid, sharp little windows way up on a building, a small green track detail on the ground, the clarity of a reflection in a truck window, even the definition of a light switch next to some stairs. Small stuff that other methods might blur or miss. And Figure 5, which shows that train scene again, but at different component counts, is particularly illustrative of that efficiency gain. You see how well it holds up even when you drastically reduce the number of components?
What stands out in that train scene comparison?
Well, at lower component counts, like say 180,000 components, which sounds like a lot, but it's low for these models.
Right.
You see methods like the original 3DGS showing significant blurriness, even improved variants like one called GES or another called 3DGS MCMC still have visible artifacts, maybe blurry backgrounds or weird random noise patches in the sky.
But SSS.
SSS, even at that lower count, clearly separates and reconstructs the sky and the distant hill. And crucially, it manages to keep the sky color smooth and homogeneous while still capturing details like the individual trees and the texture of the lawn on the hill. It avoids that trade-off you often see where capturing detail introduces noise elsewhere.
So it maintains quality more gracefully as you reduce the budget, the number of components.
Exactly. It provides consistent, high visual quality across a much wider range of component budgets.
And they mentioned some supplementary examples, too. More visual evidence.
Yeah, those further highlight SSS's knack for capturing complex details with fewer primitives. Things like fine food residues inside a metal bowl.
Okay. Tricky texture.
Yeah. Or a sharp chair reflection in a glass surface, crisp edges on walls and clear text on objects, intricate carpet texture, even subtle window gaps visible inside a woven basket.
So it's good at both smooth areas and fine details, even with fewer parts to work with.
That seems to be a key strength the sources emphasize, yeah. Handling that mix efficiently.
And just to confirm, the ablation study they mentioned, that's where they test taking out each piece one by one.
Correct.
That study confirms that these aren't just random luck, right? Each of their proposed ideas, the t-distribution, the SGHMC, the negative components, actually contributes.
That's right. The ablation study results, shown in the supplementary material, indicate that each of those core components contributes meaningfully to the overall performance improvement, whether you measure it by quality or by efficiency gains. They all play a part.
Okay, so SSS really does seem like a significant step forward in how we represent 3D scenes digitally. But let's connect this back to the listener. Why does this matter for someone, maybe not deep in the research weeds? What are the practical implications of being able to represent scenes with fewer components while keeping or even improving the quality?
Well, this kind of work is directly contributing to the fundamental building blocks of future 3D technologies, right?
Okay.
So if SSS, or methods inspired by it, can represent complex scenes really well, but using far fewer components, that has huge practical benefits down the line.
Like what specifically? Give me some examples.
Think about efficiency in the real world. Fewer components means smaller file sizes.
Ah, okay. Storage and bandwidth.
Exactly. Critical for storing these complex 3D scenes, and especially for transmitting them over networks, like for streaming VR or AR experiences.
Makes sense.
It also potentially enables faster rendering, maybe even pushing beyond current real-time speeds on high-end hardware, or allowing high-quality real-time rendering on devices that aren't as powerful. Think about your phone or maybe standalone VR headsets that don't have a beastly gaming PC attached.
So better 3D experiences, looking sharper and running smoother across a wider range of devices.
That's the potential, yes. And it directly translates to better quality and detail in all sorts of applications that rely on this kind of neural rendering.
Like VR and AR.
VR, AR, generating 3D assets from images, the whole text to 3D thing that's taking off. The sources actually mention these applications right in their introduction. Improved quality and efficiency at this fundamental level just enhances what's possible across all these rapidly evolving fields.
It sounds incredibly promising then. What about the road ahead? Are there acknowledged limitations or areas for future work that the researchers themselves point out?
Yeah, absolutely. The researchers are quite upfront about the current limitations. They note that the primitives themselves, the t-distributions, while more flexible than Gaussians, are still limited to shapes that are relatively symmetric and smooth.
So maybe struggling with really sharp, complex geometry sometimes.
Potentially, yeah. That might limit representation in some edge cases. Also, that SGHMC sampling process we talked about.
The smart learning part.
Right. It apparently requires some careful tuning of certain parameters, like figuring out the right percentage of negative scooping components to include versus positive ones. That needs to be dialed in.
So it's not quite push-button automatic yet.
Not completely, it seems. There's still some craft involved in getting the best results.
And their ideas for pushing this further. What's next?
Well, they suggest exploring combining the t-distributions with other distribution families. They mention Laplace distributions, for example.
Why?
The idea is to potentially gain even more expressivity, more varied shapes in the basic building blocks. They also plan to work on making that SGHMC process more self-adaptive.
To handle that tuning automatically.
Exactly. To help automate the process of figuring out how to balance the positive and negative components effectively, making it easier to use.
Okay, so to quickly recap then. Student Splatting and Scooping, SXS, takes on the limitations of the very successful 3DGS by really rethinking the core.
Mm-hmm.
It uses flexible students' t-distributions that can adapt their shape.
Right, the learnable.
It introduces the power of both positive splatting and negative scooping components for, super efficiency.
Yeah, especially with topology, like holes.
And it employs a smart sampling method called SGHMC, plus that recycling trick, to learn it all robustly.
That's the package.
And the results shared in the sources show it significantly improves parameter efficiency, needing potentially way fewer components, while also hitting state-of-the-art, or even better visual quality across a bunch of standard tests.
Yeah, it's a really powerful demonstration, I think, that challenging the fundamental assumptions of even very successful models like 3DGS can yield pretty substantial gains, both in performance and in efficiency.
It really makes you think. As we keep pushing the boundaries of representing our 3D world digitally, research like student splatting and scooping shows us that sometimes it's these fundamental changes, tweaks to the underlying math, changes to the learning process, that can unlock massive gains in efficiency and visual fidelity. It kind of makes you wonder what other basic assumptions, maybe across the whole field, we might need to challenge to build those truly immersive digital futures we keep envisioning.